So I said that one of the important things about vectors was that we thought of them in a special way and treated them algebraically in a special way. So points are just points, right? But vectors, we want to be able to add vectors and we want to be able to multiply vectors by a scalar. So addition and scalar multiplication of vectors are defined in the following ways. So we have two vectors, vector u and vector v. We call their components u1 and u2, v1 and v2 respectively, and then we just have some scalar c. First of all, we want to say what it means for two vectors to be equal. And by two vectors being equal, we just say that they have the same components. So the first component should be the same, and the second component should be the same. So if you think of the picture before, we had two representatives of v. They are equal because their components are the same. Adding vectors is just adding their components. So vector u plus vector v is just u1 plus v1, comma u2 plus v2. And scalar multiplication is just multiplying each component with the scalar. So here I've tried to illustrate addition. So we have here a vector v, right? And a vector u. And then what happens is if you first go u1 in this direction and then v1 in this direction, then we go u2 in this direction and v2 in this direction, we end up here, right? So one could also think of it as first going along this vector and then going along this vector, and then you end up here. And then the sum is this one. And the reason why I wrote these is that you can clearly see that it doesn't matter in which order you do this, and it reflects the fact that it's not important whether you order this in one way or the other. So that was multiplication illustrated. We could have taken a vector pointing in the opposite direction, more or less. Then you end up with very small sum here, right? So that was an illustration of the addition. Then you could also think about how scalar multiplication looks, and it's basically you just scale the vector. That's why it's called a scalar. So if the constant scalar is less than 1, but positive, you get a vector which is shorter than the original one. If it's bigger than 1, you get something bigger. And if it's negative, you get something pointing in the opposite direction. Then we have a theorem which tells us how lengths behave when you have scalar multiplication. So the length of a vector that you have scaled is just the length of the number times the length of the original vector. That's how you can read this. And the proof is just putting everything into the definition. So Cu is this vector, right? So the length of Cu is this number. Then this 2 should be outside the parentheses, I'm sorry. Multiplying Cu1 with itself, of course, gives you this, and the same with Cu2. Then both factors inside the inside the root are multiplied by c, so we can make a parenthesis like this. Then we can split the square root in 2 like this, and then we see that this is just this. A few other definitions. We define the 0 vector. We define the negative of u. The 0 vector is of course just 0, 0. So if you take one of these to be 0, what happens? Well, if you add 0 to another vector, you just get the vector itself, right? And if you multiply any vector by 0, you get the 0 vector. also, the zero vector is special in the sense that I said you should think of a vector as a direction and a length. It's clear what the length of the zero vector is, right? It's 0. But what is the direction? It turns out that it's any and all directions at once. We'll get back to that later. It turns out to be the right definition, so to speak. So the negative of u is just, let me make both of these non-negative. And then we take this. So the negative of u is just the vector pointing in the opposite direction, right? Having the same length. And it's just defined like this. Then we define, having defined addition and the negative, we can define subtraction. So u minus v is just u plus minus v. That's also how we do with numbers, right? And then we can also divide a vector by a non-zero scalar. So if you write vector u divided by c, what you mean is you multiply by the inverse of c, so that's just this. Of course, c should be non-zero because you're not allowed to divide by 0.